Hi everybody, and welcome to our module on risk quantification. Lots of the practice of medicine involves quantifying a patient's risk of disease. For example, we know that patients who smoke have a higher risk of lung cancer. We also know that patients who exercise have a lower risk of heart disease. And the way we know these things is from epidemiology studies, especially from cohort and case control studies, which I talk about the design of these studies in another video. But in this video, we're going to talk about how you can use the data from those studies to estimate specifically the risk of disease in certain groups. For example, epidemiology studies like cohort and case control studies can be used to tell us things like that smoking increases the risk of lung cancer by X%, or that exercise decreases the risk of heart disease by Y%. And so we'll talk about how you determine these things from the data from epidemiology studies in this video. The way that we quantify risk using data from epidemiology studies is by creating what's known as a 2x2 table. This type of table can be created using data from either cohort or case control studies. Shown at the bottom of the screen is an example of a 2x2 table. So in epidemiology studies like cohort and case control studies, we have some patients with disease and some patients without. We also have some patients who were exposed and some patients who were not exposed. And so you can divide the patients from the study into 4 groups and write the numbers of patients for each group in one of the quadrants on the 2x2 table. Patients who have disease and who are exposed are written where the letter A is shown here. And patients with disease and no exposure are written where the letter C is. For patients without disease, if they were exposed, that's written where letter B is. And for patients without disease who were not exposed, that's written where letter D goes here. So some of the things you can use the 2x2 table for are to determine the relative risk or risk ratio. We'll talk about this in a second. You can also calculate an odds ratio. You can also calculate attributable risk and number needed to harm. And so we'll go through how you can calculate all of these things using the 2x2 table in the rest of this video. Let's start by talking about how you can determine the relative risk using the 2x2 table. The relative risk is the ratio of the risk of disease in the exposed group compared to the risk in the unexposed group. And this can only be determined for data from a cohort study. You can't determine a relative risk from a case control study, and I'll talk more about why that is the case later in this video. So the risk of disease in the exposed group is A over A plus B. It's patients who have disease and exposure divided by all patients with exposure. The risk of disease in the unexposed group is C over C plus D. It's equal to patients who have disease but lack exposure divided by all patients who lack exposure. And so once you know these two numbers here, you can then calculate the relative risk. It's equal to the risk in the exposed group divided by the risk in the unexposed group. And so the relative risk is a number that indicates the risk of developing disease if you have the exposure versus non-exposure. So for example, if we determined a relative risk equal to 5 in a cohort study that evaluated the development of lung cancer in smokers, that would mean that smokers are 5 times more likely to get lung cancer compared to non-smokers. The smokers are the exposed group, the non-smokers are the unexposed, and the disease is lung cancer. And relative risk is a number that always ranges from 0 to infinity. If the relative risk is equal to 1, it means there's no change in risk from exposure to the risk factor. A relative risk greater than 1 means exposure increases risk. This is what you would expect for smoking and lung cancer. And a relative risk that is less than 1, like for example 0.5, would mean that exposure decreases risk. This is the type of finding you would expect in a study looking at exposure to exercise and an outcome like heart disease. And so just to emphasize this point because it's important, the relative risk is equal to the ratio of the incidence of disease in the exposed group divided by the incidence of disease in the unexposed group. In another video, I talk about how cohort studies are also called incidence studies because they can be used to determine the incidence of disease. And so once you know the incidence of disease in 2 groups, the exposed and the unexposed, you simply take the ratio of that, and that's the relative risk, also called the risk ratio. So just to make this very clear, let's go through a couple of examples. Suppose that 10% of smokers develop lung cancer and 10% of non-smokers develop lung cancer. This would be a relative risk or risk ratio equal to 1, meaning that exposure is not associated with a change in the risk of disease. If, on the other hand, a cohort study showed that 50% of smokers developed lung cancer versus 10% of non-smokers, this would be a relative risk equal to 5. And finally, if a cohort study showed that 10% of smokers developed lung cancer, whereas 50% of non-smokers developed lung cancer, that would be a relative risk of 0.2. This number is less than 1, and that means smoking is protective and lowers the risk of lung cancer, which we know is not the story in reality, but this is just an example of what a risk ratio less than 1 would look like. So in board questions, they like to give you a description of a case and ask you for the relative risk, also called the risk ratio. So now let's talk about how to do that. So let's suppose you're asked about a group of 1,000 college students who's evaluated over 10 years. 200 are smokers and 800 are non-smokers. Over the 10-year study period, 50 smokers get lung cancer compared with 10 non-smokers. So first of all, notice that this is a description of a cohort study. We're identifying patients by presence or absence of the exposure, which is smoking, and that's the way the cohort studies are designed. So I've created a blank 2x2 table here. Disease is always written along the top and exposure along the side. They tell us that the study includes 200 smokers, so I'm going to write that number here, 200, and then they tell us that there are 800 non-smokers, so I'll write that number here. They then tell us that 50 smokers get lung cancer, so I'll put that number right here. That means that 150 must not have developed lung cancer. And they tell us that 10 non-smokers get lung cancer, so I'll put that number right here. And that must mean that 790 students do not develop lung cancer who were non-smokers. So now we have all the numbers that we need to calculate the relative risk. The numerator, which is A over A plus B, is going to be equal to 50 over 200, which is 0.25, so that number is going to go on top here. On the bottom, we have 10 over 800, which is 0.0125, so I'll put that number here. And then if you do this math, it works out to be 20, so there's a relative risk of 20 as determined by this study of college smokers and non-smokers. Okay, moving on, let's talk about how to calculate an odds ratio. So an odds ratio is calculated from the data from a case control study. As I said earlier, in a case control study, you can't calculate a relative risk. You must instead calculate what's known as the odds ratio. And the odds ratio represents the odds of exposure in patients who have disease to the odds of exposure in patients with no disease. It's a number that ranges from 0 to infinity, just like the relative risk. And if the odds ratio is equal to 1, it means exposure to the risk factor is equal among patients with disease and no disease. An odds ratio greater than 1 means exposure is increased among patients with disease compared to no disease. And an odds ratio less than 1 means exposure is decreased among patients who have disease compared to those who do not. It's very straightforward to calculate an odds ratio from a 2x2 table. It's equal to A divided by C over B divided by D, which if you do the math works out to this equation here. Essentially, the numerator is the number of patients who have disease who are exposed divided by patients who have disease who are not exposed. And so if the exposure is linked to disease, there will be a very high number of patients who have disease and who are also exposed. And there will be a very low number of patients who have disease but were not exposed. And then the denominator is B over D. That's the patients who do not have disease who are exposed, divided by those without disease who are not exposed. And once again, if the exposure and the disease are linked, you would expect there to be very few patients who are exposed who do not have disease, and you would expect lots of patients who do not have disease who are not exposed. And therefore, this number on the bottom should be very low if exposure and disease are linked, and this number on the top should be very high. And so you can think of an odds ratio as sort of the opposite of a relative risk. A relative risk answers the question, among the exposed, how frequent is disease? An odds ratio answers the question, among patients with disease, how frequent is exposure? Now let's talk in a little bit more detail about the risk ratio compared to the odds ratio. So the risk ratio is the preferred metric. It's very easy to understand. It tells you how much exposure to something like smoking increases the risk of disease for something like lung cancer. But the problem with risk ratio is, as I've mentioned several times in this video, it's not valid in case control studies. And that's because in a case control study, the risk ratio is different depending on the number of cases that you choose, and therefore it's not valid to report a risk ratio. To make this more clear, let's suppose we conduct a case control study and we find 100 cases of lung cancer and 200 controls who are patients that do not have lung cancer. And then let's suppose the 2x2 table works out the way I've shown at the bottom here. For the 100 cases, half of them are smokers, so we split that up 50-50. And for the 200 controls, only a quarter of them are smokers, so we split that up 50 and 150. We now go through the math and calculate a risk ratio, and it comes out to 2. Now let's imagine we repeat the case control study, only this time we find 200 cases of lung cancer instead of 100. Everything else is the same, we still find 200 controls to go with the 200 cases. I can now make the 2x2 table at the bottom of the screen here. The 200 cases of lung cancer are split up 50-50 smokers and non-smokers, just like in the last example. And once again, for the 200 controls, only a quarter of them will smoke, so we'll split that group up 50-150. Now if we do the math and calculate the risk ratio or the relative risk, it comes out to 1.6. So as you can see, I've changed the risk ratio simply by collecting more cases for my case control study. And so the point here is that the risk ratio is dependent on the number of cases and controls in a case control study, and therefore it's not valid because it's not representing reality, it's representing the number of cases and controls you chose for your study. The odds ratio, on the other hand, does not change with the case number. Over here on the left is our first example where we had 100 cases, and I've calculated the odds ratio and it works out to 3. Over here on the right is our second example where we found 200 cases, and the odds ratio once again is 3. So this is why the odds ratio has to be used for case control studies, because it's independent of the number of cases and controls. And so I've highlighted these points in this slide just to emphasize them. The risk ratio is dependent on the number of cases and controls in a case control study, so it's invalid to use the risk ratio in case control studies. You must use the odds ratio instead. There is one exception to everything I've just been telling you on the last few slides. There's one situation where you can report a risk ratio in a case control study. When the disease you're studying is very rare, then the odds ratio will be equal to the risk ratio. This is called the rare disease assumption. For this to be the case, most of the exposed and unexposed patients have to have no disease. In other words, the disease must be very rare with a low frequency, and there have to be very few disease-positive individuals among the exposed and unexposed groups in a case control study. So let's go through just a little bit of math here. Shown at the top here is the equation for the odds ratio. It's equal to A times D over B times C, just like we talked about a few slides ago. In the middle of the screen is the equation for the risk ratio, but remember what all these letters represent. If we look at the 2x2 table at the top of the screen here, A and C are the number of patients who have disease. And so if A and C are very, very small compared to B and D, then we can change this equation for risk ratio. If A is very, very small, we can just get rid of this because B is much larger than A. And if C is very, very small, we can get rid of this because D is much larger than C. And then the risk ratio equation becomes equal to this, which is the same as this. And now we have the identical equation for risk ratio and odds ratio. And so the rare disease assumption says that the odds ratio is equal to the risk ratio as long as the disease is rare. And rare means that B is much greater than A and D is much greater than C. So using the rare disease assumption, you can report a risk ratio from a case control study, which normally should not be done, as I said before. A commonly accepted number for when you can apply the rare disease assumption is when the prevalence of disease is less than 10% in a population. And the reason the rare disease assumption is helpful is because case control studies are easier and less expensive to conduct, but the odds ratio is a weaker association, so if it's possible to report a risk ratio, researchers prefer to do that, and they are able to do that for a case control study if they can apply the rare disease assumption. So a classic board question is a description of a case control study, but a risk ratio is reported, and the question asks, is this valid? And the answer is, it is valid only if the disease is rare. So in a cohort study, the main way that risk is quantified is by reporting the relative risk, also called the risk ratio. But there are some other ways to quantify risk from a cohort study, and let's talk about those now. The first one is the attributable risk. So suppose a cohort study found a 1% incidence of lung cancer among non-smokers and a 21% incidence in smokers. Well, based on these numbers, the attributable risk of smoking on lung cancer is 20%. That's the difference between these two numbers. 20% represents the added risk of lung cancer that occurs due to exposure to smoking. So even if you didn't smoke, you'd have a 1% chance. But if you do smoke, you add 20% to your risk, and therefore the attributable risk is 20%. And we can calculate the attributable risk from a 2x2 table similar to the way we calculate the risk ratio. So I told you before that the risk ratio is equal to the incidence in the exposed patients divided by the incidence in the unexposed. Well, the attributable risk is simply the difference between those two groups. So it's the incidence in the exposed minus the incidence in the unexposed. That gives you the attributable risk, just like we saw in the last slide. So to understand why it's helpful to report an attributable risk, let's consider two studies of smoking and lung cancer. So in study number 1, the risk of lung cancer in the patients exposed to smoking was 50%, and in the unexposed it was 25%. This gives us a relative risk of smoking on lung cancer of 2 and an attributable risk of 25%. That's the difference between these two numbers. In a second study, the risk in the exposed group was 10%, whereas the risk in the unexposed group was 5%. This also gives us a relative risk of 2, but in this case, the attributable risk is only 5%. So by reporting the attributable risk, you add detail to the relative risk. The relative risk can be the same in different studies with very different attributable risks to the exposure. Sometimes, in addition to reporting the attributable risk percentage is also reported. This number represents the percent of disease that's explained by the risk factor. And the attributable risk percentage is equal to the attributable risk divided by the risk of disease in the exposed group. So for example, suppose the attributable risk of smoking and lung cancer was 25%, that number would go here. And then suppose the risk of lung cancer in smokers was 50%, that number would go here. This would give us an attributable risk percentage of 50%, and what this means is that 50% of lung cancers are explained by smoking. The other 50% are related to other factors. And you can calculate this if you know the attributable risk and the risk in the exposed group. You can also calculate it directly from the relative risk if you know that number. The attributable risk percentage is equal to the relative risk minus 1 divided by the relative risk. So let's go back to our two studies, both of which have a relative risk of 2 but different attributable risks. We can then go and calculate the attributable risk percentage in each group. For study number 1, it's going to be equal to the attributable risk 25% divided by the risk in the exposed, which is 50%. And that's going to give us an attributable risk percent of 50%. And if we do the math in study number 2, we get the same number of 50%. And so once again, this is telling us the percent of the risk of lung cancer that is related to smoking according to each study. And then another number that can be reported in a cohort study is the number needed to harm. This is the number of patients who have to be exposed for one episode of disease to occur on average. So for example, it could be the number of patients who need to smoke in order for one case of lung cancer to develop on average. It's equal to the reciprocal of the attributable risk. So for example, if the attributable risk of smoking was 20%, then the number needed to harm is 1 divided by 0.2 or 5. And this means that on average, for every 5 people who smoke, you would get 1 case of lung cancer. This is the equation shown here at the bottom of the screen. And this is similar to the number needed to treat, which is a number that can be calculated from a clinical trial. It's a number of patients that need to be treated with a drug or intervention to prevent one adverse outcome. It's calculated in the same way by taking the risk change between the groups and taking the reciprocal of that to get the number needed to treat. So back to our two studies that we've been using as examples. In study number 1, the attributable risk was 25%. So the number needed to harm is 1 divided by 0.25, which is 4, and this means that on average, for every 4 patients exposed to cigarette smoking, there will be 1 case of lung cancer. In study number 2, the attributable risk was 5%, so the number needed to harm is 1 divided by 0.05, and that's equal to 20. So for this study, even though the relative risk is the same as study number 1, the attributable risk is much lower, and therefore the number needed to harm is much higher. And that concludes our module on risk quantification.